Oh, yeah. All right, so let's continue. We're going to, today class, we're going to talk about something called normalizing flow. And so let's just do a quick recap. So previously, we talked about this, that in the concept of generative models, there are three things that you always want to remember. One is the data. I have this data, and I need to have a way to represent this data. So that becomes representation. And it's the model family, which you basically, your goal is that to find some model family that they can basically help you to represent, or basically to describe the data that you have, to learn the data distribution that you want. So, and that P of theta, which becomes that your model, basically, your goal is to compare it with your actual P of data and find a way to optimize for that so you have a lower, basically, divergence between these two. And we talked about the, basically, one of the model families we went over was the autoregressive models, which the idea of autoregressive is that anytime the data comes in some sort of like a sequential, like for example, in GPT, if words comes one word at a time, and every probability of every word depends on only on the words before. Or if you think about like a pixel CNN, every pixel comes given the previous pixel, so it's kind of like autoregressively you generate data. The thing about the autoregressive model is that they don't need a variational inference, which we saw as part of VAE. Variational inference, the definition was that anytime you have some sort of like a, for example, I have this posterior, and instead of trying to learn this directly, I basically use some basically proposed distribution Q, and try to basically use Q instead of P. That basically becomes variational inference or variational approximation. And the thing about autoregressive models is that they have direct access to the probability of the data. That's because there's no encoder decoder. It's directly every you have. So if you think about, you have a sequential probabilities. For every point you have the probability, or for every word you have a probability. So you can put those all together and come up with the total probability of the data. So autoregressive gives you that. The challenge with autoregressive is that, well, they are not that fast. For example, they are pretty slow. And then one of the other challenges that they have is the problems that you can't learn features technically over there. It's really hard to basically learn features. Then in the previous class, we went over variational autoencoders, where the idea was that in order to find the probability of the data or probability of X, we basically did some marginalization over the joint probability distribution. And we also talked about that. So probability of X is some marginal over probability of X and Z. So I'm just not writing the phi or theta, but there's a phi or theta parameters over there. Okay. And this was the general definition in basically a variational autoencoder. And from this definition, we saw that we can derive different types of variational autoencoder. So we can basically, the first thing we saw in variational autoencoder was that, well, we use this concept of variational inference or variational approximation. That means we introduce some proposed distribution QZ, and basically you have this PXZ, QZ, DZ, right? So this is basically, it's kind of like an idea of like importance sampling, right? Introduce a distribution that you're going to sample from that distribution instead of sampling from the actual P of Z. So this Z technically becomes Z's that coming from that QZ. Or we can rewrite this as, so if you think about this, this is the probability of data set, right? Technically P of D or P of X, probability of data set. And in VAE, what we are trying to do is to find some unknown parameters that maximizes this probability of data set, right? So it's MLE technically, maximizing this likelihood. So what we can do, we can apply a log. That's what we saw, and you apply log to this, then you can write this as some expectation over. So when you apply log to this term, basically it's going log of this minus log of that. So this is log of UZ, right? So this term becomes this. Why? Because, well, this is similar to expectation, right? P of P times F, so bring the expectation here. So this was kind of like the general definition of VAE. Then we also say that, okay, this general definition, this probability, this joint distribution probability of X and Z together, you can present it in different ways. So you can basically say probability of X and Z as probability of X given Z times probability of Z. You can write it as probability of Z given X times probability of X, right? And depending on which one of these two you pick, you can basically replace it here. You basically reach to a different equation for basically variational autoencoder. Then also do you need me to write those, or you know those ones? If you can replace that, right? Okay. So then we also say that, okay, this is the general definition. Now this part, you can replace it but with either of these two and simplify it. But in order to solve it, that means in order to find this P of X, and technically this is right now log of P of X because we applied log. We use the concept called Jensen inequality. And Jensen inequality basically says that if you have some basically log over expectation of something, that is always greater than expectation of log over that thing. That's Jensen inequality, right? And because we know these things, that means that I have an expectation, and I'm basically this is an expectation, right? And technically, this was kind of like a log of expectation. Well, we say that instead of we try to directly solve this because this is difficult to solve, what we do, we find the lower bound for it because we know this value is always greater than this value, correct? So the second term that over there you see, this technically is the elbow, right? Because this is the lower bound. That means instead of I directly solve for this, because this is not solvable that easy, I focus on this. I know this is the lower bound for this. So if I find my parameters somehow that increases this value, that means I increase the right-hand side, because right-hand side increases because this is larger than that. So this will increase. And what's the original goal that you have, objective function? To maximize this. So if you keep if you're able to keep maximizing this, your goal is you're getting closer to your goal, maximizing the likelihood, right? So so that was the VAE. There are a couple of things about VAE is that, well, we define that flexible marginal distribution, which is that Q, or also P of Z, we basically say that this comes from a Gaussian distribution that we sample from, so it's like some easy flexible distribution. The problem that basically VAE has, it doesn't have an intractable basically distribution over X. Why? Because if you think about P of X, you need to calculate it over all possible Z latent variables. Right? So that's in reality, that's not basically feasible. So that is one of the challenges that we have. One other thing that we saw also as part of the VAE was, I'm not going to rewrite that part, but if you remember, the way that VAE does work is you have this something called the encoder, then you have this decoder, right? So encoder, and so basically data comes here, goes through, and this basically encodes the data, then you have this mu and covariances, and then you find this mu and covariances over this is technically the z here, over that z, and then from that you sample a point. This becomes a sample, and from sample you regenerate the data basically. But there was one problem with this definition of VAE, and the problem was that this sampling part, that you need to sample to generate a point, when you do backpropagation, it's not going to be easy to solve for, right? And because you always have some sampling node in your neural network. So in order to get rid of this was this technique called reparameterization trick. And reparameterization trick said that instead of finding this as some sort of like basically the z as some sort of like a sampling, we define z as a fixed formula, mu plus covariance times some noise, right? Because now you can, so instead of having a sampling node, you just have a fixed formula node. And this noise is just a Gaussian with mean 0 and standard deviation as variance. Because now you can backpropagate through this easily, so that you don't have that stochastic nature over there. So, but again, the problem that VAE has, despite the fact that we define all this definition, is that, well, you know, the latent variables are not, because of this concept of you need to calculate over all possible z's, is not tractable. Now, the question here is that could we fix this problem? Could we basically come up with a different types of model that has some sort of like a tractable likelihood? And the answer is that yes, and that's going to be what we're going to learn today. It's going to be normalizing flow. Okay. So, any question on that so far? Right. So, this is the idea of normalizing flow. Now, it's a normalizing flow is a latent variable models, similar to VAE, they're a latent variable. That means there is a z latent variable that you want to map it to x. Okay, from some latent variable you want to generate data. So it's a latent variable models. The idea basically here is that it allows you to sample from these latent variables. You would, for example, start here from some simple Gaussian, simple distribution, you know, like a uniform or Gaussian, and reach to some complicated distribution. So imagine your data, your actual data, as some complicated distribution, and your goal is that to come up with a way that from a really simple distribution, you could transform your data until it reaches to this basically distribution. You're trying to basically learn this transformation. This direction is called the generation of the data, right? So you have a latent variable z, which is coming from some random Gaussian, and you want to be able to transform that into an actual picture, for example, right? So from just a simple vector, you want to generate, for example, a picture, right? So now ignore the formula. We will see the formula, but the idea in normalizing flow is that the P of X, which was intractable in VAE, here we will be able to directly solve it. So so in VAE, if you think about this P of X, in order to have this, you need to keep sampling from different Z and do a marginal over that, right? So you basically need to have this all marginalization. In normalizing flow, you don't have that. Right? You can directly find P of X. How? It's by how we are basically going to define this basically algorithm with these types of models. The idea here is that if we, the idea here is that we basically want to come up with some sort of model. They normally have a different, like a specialized basically architects that basically every layers of these models basically should be invertible. So you want the types of model that if you go forward, you can directly come backward without losing any information, without any problem. So that means that these types of model, they're invertible. Any function that you select are inverting. Why that's going to be useful? Because if you think about the concept of in generative models, we do two things. We do generation, we do density estimation. Generation means that I just want to be able to ask my model to generate a new data image for me. Density estimation means that I should be able to pass the data to this model and tell me if this data is real, or tell me if this data exists, right? And the model should be able to give you that density value for that, right? The challenge is that for example, in VAE, you could basically sample from Z, and from Z basically generate data. But that was easy. That's straightforward. But you cannot do the reverse density estimation. You cannot find what's the probability of an actual image, because that requires you to do that marginalization. But here, because it's going to be basically invertible, that means if you generate an image, you should be able to reverse it, basically. That's the idea here. Now, so the goal here is that you need to basically model that this distribution should be easy to evaluate. That means that you should be able to find the density, and should be easy to sample to generate from. Normally for normalizing flow, we either see unit Gaussian or you see uniform distribution as the base model, similar to what we saw technically in VAE. Now, the goal is that to map this, so this is the Z distribution over Z, to this. So this, you can kind of think of this as like a mixture of Gaussian, basically. All right, so imagine you have this data set, and your data set has images of 3 animals, right? So if you put all of those together, you have a mixture of Gaussian over 3 animals, 3 basically centroid regions, right? Center regions. So your goal is that to be able to go from one uniform Gaussian to a mixture of Gaussian that has 3 basically parts in it. That becomes the goal of the basic normalizing flow. But the idea will be that, well, what we want to do is that this flow model should be, whatever we do, whatever transformation we do, it should be invertible, right? Because again, generating might be easy as the same we saw in VAE, but inversion is not going to be that straightforward. Now, if you think about it, what you see is pretty similar to VAE. They're all basically latent variable models. But in VAE, we didn't have this part, this inversion. From Z, we map to X. Now, the goal here is that whatever mapping you do, you should be able to go back from same image to same Z. That means for every random Z, random basically latent variable that you select, you should be able to generate an image, and you should be able to go from that image to back to the same latent variable. It should be one-to-one basically mapping. All right, so that will be the idea. Now, in VAE, we do the same. We had this latent variable that comes from some simple Gaussian, and then we transform it using something like that. So we found this mean and the covariances. We pass it to a neural network. We found it, and then we using that, we did a sampling. This is example with the sampling part. Sample from a Gaussian with that mean and covariance. And then we basically using that, we find P of Z, P of X. And then what we found was that, well, this P of X is expensive. We cannot do that. So, any questions so far?
What is exactly the difference between the inversing and backpropagation? Like in VAE,
inversing and backpropagation. So backpropagation is about training your model. So you have this model, you have some parameters in your neural network, and you want to be able that neural network basically. So I have a neural network here in this one. And this neural network basic goal is that it has some parameters. In backpropagation, you tweak those parameters. So this encoder will be able to basically create this contextual representation in a good way. And this decoder, you also tweak the parameters so it can get a Z and reconstruct the data, right? But what we are talking here is that if I have an image, this image should exactly give me same Z, not something else. It should be a one-on-one mapping. So this is a different, one of what you say backpropagation is about the model training. This is about the relationship between the sample data, the base data, and the data that you're generating.
So what it is that we are trying, what it is the problem with VAE that we are trying to actually
That's the problem.
Like the inversion. Oh.
You can generate data with VAE, but you cannot basically find the density of data. Or you cannot do, for example, something like an anomaly detection, if this data is real or fake, for example, because you can't do this. It's not tractable, right? Also, the VAE, they are strong models, but the quality of the images are not that good.
But in VAE, I think maybe there is a way for us to say that if we have an image, it's from the right distribution. Because if we use the encoder, we get the P of Z given X by the encoder. I mean, for the generation, we don't use that part.
For the generation, you just need a Z.
Yeah,
From Z, you basically go to decoder, basically you generate.
but I think there is a way around it with VAE because if we use the encoder, we get a probability. We get a Z. Yes, but we already have a sigma and mu. It's trained, right?
Okay,
And
so
if that Z is outside the distribution of that sigma and mu, then that's not the right image.
So let's talk about one thing. So let's say I have this image and this part, the bottom part is known, the upper part is unknown, right? And you want to fill these pixels to make it possible. So this data, after you filled it, let's assume you filled it fully. This image should have a density value, P of X, correct? In order for you to calculate this density value, what do you need to do? You need to see all possible combination of pixels here, correct? And where are those coming from? Those are the integration over Z. Those possible combinations, Z is the latent, basically, pixels here. In order to come up with an image, so if you think about, you have 10 pixels and every one of them is binary, right? So you have, how many combinations you come? 2 to the power of 10. So just think about it. The number of combination that you comes, this integration becomes really difficult to calculate. Right? So VAE has that challenge. This is not solved. It actually has that problem that you cannot find this directly. So now let's go to normalizing flow, and then basically the idea in normalizing flow is that, yes.
Go back a couple of slides. There was a T, I didn't understand what it is exactly.
Which one?
Back. Yeah, this.
Is time.
What is time here?
The steps that you go through. In order to
We have-
change this, to this, you go through a series of steps. It's not basically, you don't go through one shot. It's like a couple of steps.
And is
Every-
it a hyperparameter? That-
He is just, you can think about it like a trajectory. Like it could be, how long will it take for your model to map this? How many iteration takes for your model to map this to that? Right? So let's say T could be number of layers that you go through it. Every layer does one transformation and you go through it.
Hyperparameter.
Could be. I mean, if you think about it, if you look at it as a layer perspective, yes, it could be. But if it's not a layer perspective, because this kind of like what we're going to just see, it's going to be like some sort of like a recursive functions, right? There's going to be a function over a function over a function over a function. So that T could be, you have this recursive until you reach to the actual, basically, distribution that you're looking at. So
And how do we understand that it is the actual distribution?
you guys need to wait. You're going to get there. We haven't even started the normalizing flow. All right. Okay, so let's just stop. We will have the answer for that. Okay, so now the idea of normalizing flow is that, well, we want to ensure that we can map Z to X. So we define this function f that when you pass Z to it, it will produce X. Okay. So the idea was that, well, we want this to be possible. We also want it to be invertible, right? That means you need to also calculate Z as inverse of X. So that's the goal that you have. You want basically not a goal, actually, that's basically the selection choices that you have. You only can pick functions that are invertible. Otherwise, you cannot solve it like that. So if you think about it, we can write this also this way. So X could be written as F inverse X, right? And Z basically becomes F inverse F Z. Okay, because it's just the inverse of, it's the same function. You can keep applying it. It should produce the same thing, basically. That's the idea. It should be a deterministic conversion. So now, f of z, whatever function you pick, it should be monotonic, it should be deterministic, and it should be invertible. And again, a unique z exists for every x and reverse. Okay. Now, the benefit of something like this is that you don't need to anymore to have this mu and covariance that goes through a neural network and you sample from and to generate a z. You basically eliminate the need for all of those. Okay, so you don't need that. You basically directly pass z to a function, and that will basically gives you the data that you're looking for. Okay. Now, so what you see here is just example of 1D.
I didn't follow. Why does the need for mu and beta go away?
So here, in order to find z, you have this mu and z,
Okay.
and you sample from that Gaussian to find the z, and from that z you go to an x.
Okay.
Here, what we say is that it's not stochastic anymore, it's the deterministic. I don't need to sample from somewhere. There's one z that goes to this x, there's one x that goes back to that z. So it's not a stochastic nature. So now in a 1D scenario, so what you see here, there are three images. One of them on the left is base density, which is z, which is the simple Gaussian. On the right is x, what you're hoping to achieve, basically that the distribution of the target. And in the one in the center is that function, basically, that we are talking about. So the first thing you want to notice that, just focus on the center. This function should be monotonic. That means it's always basically increasing up or down. It's like kind of like, it doesn't have a flick, like a up, down at the same time, just one direction. So the way that also you can look at it is that for any z, z goes to this function and it provides you the corresponding x, and this becomes the distribution over x. Okay. Now, there are a couple of things that will describe how from left we reach to a distribution that looks like on the right. Okay, so the most important part is that here, these two arrows, for example, if you look, these are the two random samples that we generated from this distribution. And these two will have these locations on the right picture. How those locations and basically why those locations, like why one of them is taller, one of them is shorter, that is actually related to this function, the derivation of this function, the slope of this line, basically. So for this point, z, this is that z, and this is the other z. So you basically, we will see the equation, you will find a slope, the gradient of this line with respect to z. If the slope is basically sharper, basically, what happens basically, if a slope is larger, it's kind of like it compresses the region. If the slope basically, if the slope is what do you call it, lower, it stretches basically the region. So now, I think we have another image that describes that stretching. Maybe that's easier. This is a reverse one. I think that's a good image. We can use this. Okay. So in order to understand that, basically, first think of this. So this point, the blue line that you see on the base density, that's one sample that you have. Now, what we do here is to kind of like break down the Z into buckets. Okay, like equal buckets, basically, like a same length buckets. Then, when you are looking at this point, this will correspond to this part of the region, part of the line. Okay, so the first thing you see that the transformation, this basically becomes wider here. It stretches in the region, right? So from here, smaller, you actually went to a wider region. Then you also have the height. With that height, will calculate it based on the probability value. So the height of the region is based on the probability density, but the width of the region is actually based on this concept of the gradient of the line. We will see the equation, but this kind of like when this is like a sharper, right? That means that you have a higher slope. This becomes wider here, stretches. When it becomes lower, this becomes smaller in the other side, kind of like this transformation. So your goal is that to transform the data from basically a simpler region to more basically a complicated region. And we will going to focus on this as transformation. I have some geometrical concepts behind it. Just bear with me on this one. But overall, basically, this becomes the idea. So you have data from left side, you sample, that sample goes to some distribution, it has a corresponding X on the right side. And because it's basically like a deterministic, so it's kind of like a one-on-one mapping, and you can reverse it back. So now, something also to keep in mind here is that this transformation and this changes into stretching or compressing the region, we basically have that because we want to ensure that this is a valid distribution to sum to 1. So if you just simply convert this to there without stretching and compressing it, there's no guarantee that distribution will sum to 1. So in order to become a valid distribution, that's why we have that compression or basically stretching. Now, so now the degree basically, the degree of by which this f of z stretches or compresses basically, that's a definition of Jacobian, right? So the Jacobian of a function basically tells you that for a given point, the Jacobian tells you that by what degree that around that point, the function will be stretched or compressed technically. Haitian tells you that by which degree around that point, by how much around that point, the gradient is changing. So Haitian tells you that how quickly around the point the gradient will change. Jacobian tells you that around the point how much you stretch or basically compression that you have. So that's basically what it tells in the first line here. The degree by which this line, this function is, or that line basically stretches, it comes from technically the magnitudes of the Jacobian. Okay. Now, if there's a small change in the input cause larger change in the output, it will stretch. That means large gradient. So large gradient, if you have a large gradient, that means if you perturb the data by a little, the output is drastically changing. So that will cause the conversion to become a wider on the target distribution, wider region. However, if the small change basically causes to a smaller output, that means low gradient, then even if you are in the base distribution, if your base distribution was kind of like a larger region, on the target distribution, this compresses, becomes a smaller range. So it depends on the magnitude of that gradient that you have basically. Now, all of these definitions, so one of them basically is about just stretching the value. So we defined, if I remove that, sorry. We defined this, okay? That's when you want to do deterministic mapping, okay? But then also, we want to map probability of z, the distribution over z, to probability over x, p of x, okay? That's what also we want. And we find this using a basic technique called change of formula, right? So change of formula, basically, this is what it tells you that. probability of X, you can be calculated from probability of Z. So probability of X technically becomes probability of Z times absolute value of determinant of that Jacobian of Z inverse. Okay, so the term in this is Jacobian. There's also determinant. This is supposed to be there's determinant basically inside. So probability of Z base times basically inverse of inverse of like a determinant of the Jacobian, like a positive of determinant of Jacobian. And we're going to also break this down, why inverse, why determinant. But so that's a fixed formula for the change of variable formula. Okay, so not just for normalizing flow. Overall, change of variable formula. If you have X, you want to go to Z, and you have something like that, you can calculate the probability of X with this definition. Okay, now this, if we want to map this back to the image that you saw, this part, this basically this Jacobian, this part, this is the width of the line. Okay, the stretching part. That comes from the Jacobian, the gradient, basically. The height of this, which becomes the density, comes from multiplying the density of Z times this value. Okay, so the height in the image is this value. The width of this line, the stretch or compress, comes from this Jacobian. Okay, so you need two pieces. One piece is that direct mapping, which I have a function that changes Z to X. Because I have that function, I know if I want to go from Z to X, how much I should compress or stretch the region based on the gradient of this function. Okay, that's the Jacobian part, which becomes the slope of this line. After that, after you find this stretching region, you're like, okay, how should I find the height of this distribution? And that comes from this formula, change of variable, basically. Yes.
Can we understand this with eigenvalues and the way we're stretching it?
I don't know if I can answer that.
Well, it would be reasonable to understand it that way.
Eigenvalue. I don't have an answer on that, to be honest. I don't know. Don't even know how to connect it right now with for eigenvalue.
Basically, you're using the determinant of the Jacobian. So Jacobian probably would give us some information. And
No, the reason we use the determinant of Jacobian is we're going to get a more geometrical, basically, reason. So the Jacobian, we'll talk about that again. We said that how something changes around the point, right? Why do we use determinant? Determinant, what does determinant tell you? Determinant tells you that the area,
yeah,
the area covered by a matrix technically, right? So if you think about this inside the parenthesis, the determinant, that's the area, correct? Right? And this is what they call, this is density, P of X, right? P of Z is density, right? What's the relationship between density and volume or area?
The integration of density.
Inverse.
Is inverse, right? If the volume is more, right, the density is lower. If density is higher, the volume is lower. So that's why you have an area, correct? If the volume of this area is high, what does that tell you? That tells you that, well, you have basically a stretch region, right? So you inverse it because the P of X, the density, then need to become shorter. Because if think about this, you have a fixed value, right? This is like the P of X. Now, if you pick this P of X and you say that I'm going to just reform it, I'm going to stretch the width. So if you stretch the width, well, the height should go down because it's inverse. Okay. We have a slide on that, but the reason for determinant and inverse is basically geometrical. All right. So this. Okay, so let's go now here Okay, so the what you will going to see moving forward. I'm going to remove this for a moment. So instead of basically, we said this is equal f of z. We also say z equal f inverse of x. So moving forward, you're going to see h. Okay, oh, sorry, z or h of x. This is going to be the same thing. So it just if you see h of x, this actually means f inverse, basically, just for simplicity. Okay. So now we are basically saying that p of x, probability of x, using change of formula, basically change of variable formula, comes from probability of z times basically inverse of hx prime, derivation of that inverse, basically. Okay, so that's the same thing you just saw. We just instead of writing this, we just put h. Inverse means you calculate the Jacobian of that, basically. Okay, the derivation of hx. Is that confusing or does it make sense? Make sense? All right. So now, let me see if I had an example before. To add something that we move from here. So if you think about, because if you think about this, should be invertible. So you can basically write both of this probability of one based on the other one. Now, in the book, you will see different definition also in your slides. So for p of x, we can basically rewrite it. Instead of z, basically we can use this value. So basically becomes probability of times. And that here also becomes the same thing, determinant of gradient of f. X. This one also, instead of p of z, we can just p of x. We can write p of f. F of d. Okay. And there are a couple of ways that we can again rewrite these ones. So the if you think about determinant, determinant is for what's the relation between determinant and inverse? Inverse of determinant.
Inverse is something of that complicated metric over determinant.
If you have a determinant of an inverse matrix, could you write it as determinant of a matrix inverse? Right, it has a relation, right? So this basically becomes p of f prime of x, determinant of gradient of f of x, inverse. Basically, bring the inverse outside. You can basically also write this as Oh, yes.
Is it inverse or f dash, like
Should be
data,
inverse, right?
it's
This-
p of,
This
P of
one,
Z.
this one is, no, sorry, this one,
is
yeah, this one is inverse, sorry.
p of z, right? Z is f inverse
Let
x,
me see.
Fine.
P of Z, we instead put, F prime,
f inverse.
no, F inverse, there should be an F inverse, right, you're right. So, even for this one, so you can still think about it, you can basically reverse this, so instead of gradient f of z, you can write gradient of f inverse f z with respect to gradient of z and then expand it. So you, in the book, you will see different definitions like a rotation. They all kind of like the same thing. It just depends on how you see it. But I think the most common one, so this is going to be same thing as we have over here now. So you just have an inverse outside also. Now, if you go to here, the geometrical refresher of all of this, see why this is happening. So basically the example here for, we're going to do 1D example. Think about, you have a uniform random variable z, and z could basically, Z could create like a cube for you, okay? I'm sorry, not a cube, like a square. Z could be in a higher dimension and basically create a cube, right? And so on. So this basically what it basically tells you that. So hypercube, when it goes to higher dimension, this is going to be a square, right? For Z. Then you have this X, which is defined as A times Z, and A should be something invertible. So that means W is going to be A inverse. This is assuming some matrix, okay? So if A times Z becomes X, you should have be able to find the inverse of A. So that means you should be able to write Z equal WX. It should be reverse basically. Now, basically what it says here is that geometrically, matrix A will transforms this square that we have into a parallelogram. Okay, so when you multiply this is Z that you have. Okay? Z could be 2-dimension, could be 3-dimension, and so on. When you multiply it by A, it transforms it into this, which is called a parallelogram. Okay, now, so let's just break this down. So think about A as a just 2x2 matrix, and Z could just be a vector of dimension 2, okay, for this square. So you have 2 points, Z1, Z2, right? And you have this matrix A, which has 4 dimensions. Okay, A, B, C, D. That's matrix A. Now, what will happen here is that how do you find these corners? You basically need to, for every corner that Z has, multiply it by matrix A. Okay, so if you pick, for example, 0 and 0, when you multiply it by matrix A, it becomes 0 and 0. If you pick 1 and 0, when you multiply it by this, becomes A and B, right? And so on. So you find this new shape, new basically parallelogram, that becomes X that you have. Okay, so that is the X. Now, is that clear so far? Now, X, that parallelogram, the pink region, has a volume or has an area, right? And we find that using the determinant. Okay, so yes, so we want to basically look at this this relationship that we're talking about. So this area for X, this inside, basically comes from the determinant of A. Okay, the modular basically of determinant of A. If the determinant is positive, that means the transformation is basically like a kind of like in a positive direction. If determinant becomes negative, it's like flipping. So if you have your determinant of your matrix A that you're multiplying, basically if it becomes negative, that means whatever you're multiplying, what you get is going to be a flipped version of the other one. over a certain axis, for example. If it's positive, that means it's a positive, basically rotation. Positive transformation is not a rotation over any axis. So that's why we put this modular around it, because it's possible to be negative or positive, but from the area perspective, we don't care about positive, negative. You just want it to be positive area. So, yeah. So, okay, where we were, we just talked about all of this. Now, probability of data becomes probability of Z basically times this determinant of W. Well, determinant of W, we know W is inverse of A. That means determinant of this is equal to 1 over A, y over inverse of y, 1 over let's write determinant of A. Okay, it's kind of like inverse. So let's stay on this before I go here. But so what will happen here is that when you do transformation, there is a relationship, direct relationship between, again, the density and basically this area. When the area is larger, right, so the density becomes lower, and that's why this becomes inverse over determinant. When you do this transformation, if the density basically is, or if the area is smaller, then the density become larger. Or when you calculate this, that the denominator basically. Now, if you think about one example here for this change of variable formula, let's say we have Z. Z is a uniform with parameters 0 and 2. And then we are saying that we have this variable X. We say we have this, X is 4Z. We say P of Z basically is 1 over 2 for range 0 and 2. Okay. Now the question here is that, well, what if you want to find what's the probability of X being 4? Okay. So you know the relationship that X equal 4Z. Now, what if you want to find what's the probability of X being 4, right? And incorrect approach to solving this is the solution that you see here. Basically, we say probability of X being 4, X equal 4, X equal 4Z, and that becomes 1 over 2, right? But that's not a valid approach because that doesn't account for the when you change this from one distributed variable to another variable, the density value should either stretch or decrease depending on that determinant, that volume basically of the space that you have. So what basically you do in the change of variable formula, basically you say that, okay, I know X equal 4Z. That means I know Z equal 1 over 4, basically X. So this is the Z that you have. So if you want to find probability of X, technically is probability of Z times basically this derivation of this term, X over 4. Because remember, it was the modular over basically this derivation. So this becomes times 1 over 4 because we know this is 1 over 4, right? So in order to answer the question, you basically say is that, well, I need to find what is the probability Z H of X, because this is a uniform and for all of this is 1 over 2. So you have 1 over 2 times 1 over 4 becomes 1 over 8. So the correct answer for this probability of X being 4 is actually 1 over 8. Okay, so the point here is that if you do, when you do change of variable, you need to account for the changes in the distribution shape. Is not a direct change. So the distribution either becomes wider or becomes basically shorter, right? So you need to account for that. And you do that by basically looking at this inverse of the this derivation. So another example for that is, let's say you have f of x to be, so we are saying that here, x is equal to f of z and it's an exponential. So exponential over z. And then the question here is that, okay, what is the, for example, p of x? Simple scenario is that, well, we know basically x equal exponential over z, so we can find z to be inverse of that, becomes ln of x, right? So basically, whatever is the probability of z times derivation of the ln of x, basically, and that basically reach to 1 over 2xy. So z is between 0 and 2, right? So that means probability of z is 1 over 2, correct? So, and then if you think about ln of x, the derivation of that becomes 1 over x, right? So you have 1 over x times 1 over 2, 1 over 2x. So that becomes the derivation, basically that becomes, sorry, the probability or the density of x, basically, mass function of x.
What PZ, and X, how do we calculate that one?
So you always need to remember the relationship that, what I wrote here, you can constantly swap this terminology. So we are saying that probability of x equal, this is a change of variable formula, just memorize it. Probability of z times the whatever is that gradient, for example, inverse. Okay. Now, instead of z, what is z? Z equal x equal exponential over z. That means z equal ln of x, right? So probability of z, instead of z, you put ln of x, basically.
Yeah, but I don't know how to calculate PZ of ln x.
That means in a reverse way, basically, that is still, what's the probability of z? It is uniform, correct? What's the probability of z? This is the same thing. It's always 1 over 2, right?
Oh, it's uniform.
It's uniform. So it's 1 over 2 times, what's the gradient of the h of x, which is ln x?
X.
1 over x, 1 over 2x, right?
Yeah,
It's kind of like a,
uniform.
yeah. All right.
You just wrote that the inverse of the h prime of x, but
So
here, which one is
that-
correct?
Okay, I need to write a different term. So instead of h prime, I need to write f.
F, okay.
Sorry, this is correct, f. Because h is inverse of f, so I don't, if I put h, I don't need the inverse anymore. That's correct, thanks. All right. Now, so now let's map all of this to basically what we are trying to do in normalizing flow. So in normalizing flow, there are two directions, okay? One is a generative direction, a forward direction. One is a backward direction or inverse direction. So in the generative direction, or basically forward direction, this is basically what you saw, f of z, x equal f of z. That's a generative. For basically random latent variable, from a random latent variable, you pass it to a function and you get n data. Right, so that's the generative direction. That becomes the first part. The second part, which is the inverse over, your goal is that from x to regenerate basically the z, that latent that you have, that's called normalizing direction. And that's where is normalizing flow comes, basically. The generating part is similar to VAE or other techniques that you have, it's just generation. But the idea then in this normalizing flow is that we want to be able to go from a really complex distribution, which is x, go back to a really simple distribution, right? And if you think about what was the definition of z comes from some simple Gaussian, right? So we want to normalize that complex distribution back to a simple distribution. So that's this, and if you go back to, this image, normalizing flow becomes this direction from here to here, basically. Being able to pick something complex and normalizing it to something simple. That becomes the normalizing flow direction. So generation becomes reverse part, the normalizing flow becomes generation becomes forward pass, normalizing flow becomes the reverse pass, basically. Any question on that? All right, so now, what the image that you see here, this is kind of like the same image we saw before, but in a reverse basically direction. So first here you have the image on the left, which is the target or the model basically distribution, the more complex one, and you want to be able to go back from here to here. Okay, and this basically same concept applies here. So you have x from -3 to -3. Then you have z from -3 to -3. And what you see here is the inverse of the function. So the way that it makes it easier, at least I hope so, is if you go back to this one, this is the reverse of that. What you will notice is that the main change is in the function. So here, x equal f of z. And you go from z to x, correct? In the reverse direction, the function is inverse of the previous function, basically. So if f inverse, basically, the other one was x equal f of z, this is z equal f inverse. And the relationship is still going to be the same concept. The slope, right? The slope of this function with respect to x on the other side is the slope of that function with respect to z, because that function gets z as an input. So here the function gets x as an input, so you get the slope of function with respect to x. Based on that slope, you know if this beam is going to stretch or going to be compressed. And in order to find the height of this same thing, this is basically what it is. The one on the bottom is the reverse version of the one above. Probability of z defines the height of the bar, comes from probability of x times this, and then you add change of variables. You find the inverse. Basically, this means f of z becomes f inverse of that, and you take a derivation of f inverse of that with respect to x, basically. Okay. So, any question on that? Is this clear, or is you guys getting lost? Which one?
It's clear
Clear?
and we are lost.
It's clear that you're lost?
No, it's clear, but we are lost.
Alright.
Clearly
So-
lost.
Huh?
Clearly lost.
Clear lost, all right. So, hopefully when we get closer or as we go, you guys will pick it up. But yeah, it's not going to be a straightforward concept. It's most of the algorithms in vision are less clear in compared to NLP. NLP is kind of really a straightforward concept. Vision is kind of like things are not that straightforward, because if you think about it, the qualities are like much what you generate is actually need to be much better. In image, you just generate languages. It's kind of like it's a bit different.
Why do
Sorry,
they
in
call it
NLP.
vision then?
What?
Why do they call it vision?
Yeah. So now let's talk about learning. So we just defined a framework so far. We haven't actually got into the normalizing flow, the architects of this model. But how we are going to actually learn this? Well, the learning, you can think about it like a maximum likelihood estimation. So your goal is that to find some parameters of some model, that some neural networks that you have, for example, that maximizes this total, basically probability, right? Or this total likelihood. So this per data point, right? This is likelihood per data point, assuming these are IID, this is multiplication. One thing you could do here is that, for example, if instead of maximizing this, you could minimize the negative of that. You can apply log also to, make it a summation. Now you have log over P of X. Now, one thing that we could just so we are trying to find some parameters. Again, here it always was some parameter. I just didn't write those. That maximizes or minimizes the log of basically this summation of the log over P of xi given this, right? That's what we are trying to do. So this itself comes from this definition, right? Change of variable formula, probability of x comes from probability of z times that compression or basically stretching. So if we apply it here, if we apply log to this, becomes log of this plus log of this, right? So technically this becomes arg mean summation log of P of z plus log of basically this isn't. So this is, if you think about it, is inverse, right? So it's like a 1 over that value. So log of 1 over becomes log of 1 minus, so get rid of the 1. And so there's also a negative here because we did arg mean. So this becomes negative. This is already a negative because it's 1 over. And when you multiply it by the other negative, becomes a positive term. That's why you basically see this, basically the log of this determinant of this Jacobian, basically. Okay, so whatever you have here is going to be the Jacobian with respect to what we call Ci. Okay. So that's, again, that's how we got to that point. It's technically 1 over that term. When you apply log of 1, you get rid of it, becomes minus log of that Jacobian. And so this is the Jacobian. I just wrote it as J. Yes.
Why don't we have the determinant?
So it's we have it. It just for
Because you didn't write it.
no, we have it. So it's for simplicity. It's kind of like for simplicity. It has that determinant value. So yeah, some of the slides. Sorry, it is there. Some of the slide is not there. It's just that typo problem. But okay, so now let's map this to and basically 1D example. So how does this model like this work? You basically what you want to do, you want to sample Z from some base distribution. You should be able to pass Z to a function and you should be able to get X. That gives you the data point. Then you should be able to answer the probability of that data point, the likelihood of that data point by doing this. So you first find the data, then you're like, okay, what's the likelihood of this data? And you basically say that the probability of Z based on the sample that you picked from the distribution. Because P of Z you have is a Gaussian, right? So if you sample from it, you also know what's the probability of Z, the density, right? So you have that. This part, it's you have a function, you take a derivation of the function with respect to that Z, find the determinant, inverse it, multiply it by P of Z, that becomes the likelihood of the data that you generated, the image that you generated, basically. Okay. So there are 2 steps. One is to sample from Z, pass it to a function, get X. That's your generation. The other one is that what is the likelihood of this? Like ask a different question. How likely is this image? Or how likely is data? Then you can find the likelihood of that data by multiplying the density of the Z, the latent, times inverse of the basic determinant of the Jacobian. Okay, that becomes how likely is that that data. All right. Now, if we go to okay, there's a couple of good points here. So let's start with the invertible matrix A. If you have an invertible matrix A, determinant of the inverse A inverse becomes determinant of A inverse. That's one thing that we just talked about. The one thing about normalizing flow is that X and Z should come from same dimension, because you do a direct transformation, right? In VAE, there was no reason. Remember, we actually break down the data to a much smaller maybe dimension and then regenerate from there. In normalizing flow, that's not the case. Z and X should be same dimension, basically. Okay. The other thing is that when we talk about the Jacobian, so this is the Jacobian of the, for example, a function that you have. The Jacobian basically measures the local scaling factor of this transformation. And that comes back exactly what we talk about. So Jacobian tells you that how this transformation scales z. So you basically, when you have a z, you pass it to a function. The Jacobian tells you that this function is going to scale z by this much. Okay. Now, on the other end, the determinant of the Jacobian tells you that how much this function basically scales the volume of z. Okay, so Jacobian tells you that how it will scale the z. Determinant of that tells you that how it will scale the volume of the z. And that's because we also know that because the volume and basically the density, they have an inverse relationship. And that's why basically it becomes inverse of the determinant. Does it clear some doubts that you had?
So I have another question. The whole reason that we wanted to use the encoder decoder was that to break the data into smaller amount of data. Like when we have an image, we can transfer it to a vector. That is much easier to understand and train.
Not necessarily.
What?
One of the reasons for the using
Was that?
autoencoder is that, yes, one reason is that if I want to extract features from the data that I have, and I want to do something, maybe clustering or visualizations on a lower dimension, then that Z becomes important,
And
right?
it's easier to train.
Easier to train depending on what type of autoencoder we're talking about. If we do just, for example, autoencoder that just doesn't do any generation, it's easier to train. If you do autoencoder that's generative, like variational autoencoders, they are not easy. So a straightforward from training concept, but they are not easier because that the result that you get doesn't mean that it's a good model. Like there are lots of tweaking actually you need to do in these types of models. Right. Even variation, even this normalizing flow, or as we go through chapters, you will see that most of this algorithm, they kind of actually have lots of tweaks in order to actually make them work. That's why kind of like they're more difficult in vision in compared to maybe NLP, because there's kind of like a straightforward. Here you actually have lots of challenges in generation or inversion. But yeah, so what you're saying that yes, to some extent is correct that yes, if you want to just get a lower dimension data, autoencoders are great. But in variational autoencoder, which we use it as a generation, one of the reason we break down the data is because we wanted to see that if we can learn the underlying distribution, that if we could break down this data to a really simple Gaussian, and we sample from that simple Gaussian and to regenerate it. So that was the goal over there. Like, but you don't necessarily need in autoencoder actually go to a lower dimension. You can actually have autoencoders that they are like this. So autoencoders basically also exist like that. The way that these types of autoencoders work is that this latent variable that we introduced has a lots of sparsity actually in it. It's like a lots of sparse points. So these are like an architect choice, basically. So, all right. So this is the overall, basically, definitions. Now, again, to summarize, probability of X basically comes from the probability of Z times inverse of determinant of the Jacobian. Then, what basically says in the last line, this basically ensures that the total probability that you get for P of X is a valid probability. That means it will sum to 1. If you don't have this inverse of determinant, it doesn't actually sum to 1. It's not a valid distribution. So you need this basically in order to sum to 1 to become a valid distribution. You need to scale it, you stretch it or compress it basically. Now, if we go to a 2D version, for example, here, let's say we have a Z1 and Z2, two variables, like like this one. We had Z1 and Z2 are two variables. And then we have this function U that basically is a transformation. So U at any point could get Z1 and Z2 and will produce an X1 and X2 basically, okay? And V will be inverse of U as a function. V is the inverse of U. So you can basically write V as U inverse, basically. Okay, so that's what it means. Now, the change of variable formula for the probability of X basically tells you that probability of X1 and X2, here you have only 2 dimensions, comes from probability of Z. Instead of Z, we are writing V because was the inverse, right? That comes back to here. Same thing that here we had exponential, and instead of Z, we wrote ln Z, which is inverse of exponential. So inside this parenthesis, instead of V1 and V2, you can just write U over X1 and X2 and put the inverse on top. That is equivalent of V over X1 and X2, because V is just simply inverse of U. Okay? Does that make sense? All right, let's write it on the board. So let's say we have, let me see, we have U is U1 and U2, okay? And then we have V, which we have defined as V1 and V2. So we have Z1 and we have also Z2. From Z1 and Z2, we are producing X1 and X2. So X1 and X2. Now, how are we producing X1 and X2? Basically, we have this function U that you pass basically 2 points to it, and it basically gives you another point. So basically X1 could become U1 Z1 Z2. A function, you pass Z1 and Z2 to a function and gives you X1. You have X2 comes from U2, Z1, and Z2. Okay. So now the question basically tells you that if you found this X1 and X2, can you tell me what's the probability of X1 and X2? And we say that yes, using the change of variable, basically we say this is equal probability of Z over technically Z1, Z2 times inverse of whatever was our function, which is U Z1 or UX1 or Z1, Z2, and inverse with respect to Z1, Z2, Z1 and Z2. There's like twice basically. This is Jacobian technically, and there basically you could bring the inverse also. There's also determinant. Okay. Now what you see on this slide here, instead of Z1 and Z2, you basically use what definition you had here. If you pass Z to U, it will give you X, correct? That means if I do U inverse X1 and X2, U1 inverse, sorry, U1, because we have U1 and U2, that should give me Z1, correct? If I do Z2 equal U2 inverse X1 and X2, correct? This is equivalent of just simply saying V over X1 and X2, V1, V2 over X1 and X2, because these two are just inverse of each other. So what you see on this slide, instead of writing U1 inverse Z1, Z2, I've just put the V because V is defined as inverse of this. They're identical, they're the same thing. Okay, so this term and this term are the same. You can both use either one in the parentheses. And here, basically, you have the determinant of this Jacobian. The reason you don't see an inverse here, because we already use V. V is the inverse of U. If you use U, Jacobian over U, then you have an inverse outside. Okay, so it's kind of like, these are all coming back. What I wrote. I removed it. That I told that in the book you will see different combinations depending on which one you are using. You're using U or using V. If you use U, you need to put an inverse outside. If you use V, then you don't have an inverse because V is defined as the inverse of U itself. So it's kind of like your choice. So, so here now the first term, what you see here, the first term, which is this probability of Z1 over this, just represents the density over Z1 and Z2. Okay, that's the density value. The second term is kind of like a correction. Basically, it tells you that, well, that is the density, but because of this transformation we did, that density either stretches or compresses. So the second term basically is kind of like a correction term for the density that you find in order to find this density. Okay, so again, just maybe that becomes the learning for today's class. Change of variable formula, it has two parts: the original base density, density probability, and some correction term for stretching or compressing, basically. Now, this is the other version of it. If you use U, then you have the inverse outside of the matrix. Okay. Again, this is simplified. Otherwise, it should be U1, X1, X2. Right. Now, now let's go to the forward mapping. So the idea of forward mapping here is that you start from Z, the base distribution, and you map it to a basically more complex, basically transformation. And it's actually called planar flow. You basically go from this to this, like a planar, basically distribution. Or you go basically from this uniform all the way to this more complex, basically distribution. And these are all possible with this normalizing flow concept. And the beauty of something like this is that, well, what you see on the bottom, the formula on the bottom, X is a function over Z. And that comes back to the question you asked at the beginning of the class, that what is that T? What's the number of iteration? It's kind of like a recursive operation until you reach to maybe what you define as a good learning. You could be fixed. You could have K to be a basically fixed number of iteration, or you could basically learn it over time. You know, kind of like recursively going over the number of iteration to see that where should you stop. But this overall defines this process. The beauty of this is that you are able to reverse this to go back to the original distribution. So if you do inverse over the formula in the bottom, X equal that F of, basically, this is what you get. So Z becomes F inverse of X, which is F inverse of all those basically recursives. So starting from the inner part, which is, sorry, starting from the outer recursive in the forward pass, you go all the way back to the inner recursive in the forward pass. So it's kind of like a reverse, basically, of the recursion.
In the previous picture image, there were a couple of brighter regions in the last iteration, like those reddish circles in the last, like M equals 10.
This one, you mean?
Yes.
So that's a density.
So these reddish circles, they should match with the number of variables dimension, right?
No. So that's such a great question. So what you find from the number of like a circle or islands or polar basically that you find over there, those are not about dimension. Those are about actually concepts. How many concepts you are finding in this data? Imagine I'm doing basically learning images, and you basically saying that, well, there's for an image, there's a distribution over things.
Pixel, second pixel, third.
No, not pixels. It's over concept like gender or color, hair, or things like that, basically.
But because the whole normalizing flow keeps the dimension the same.
Yeah, so this is the dimension. The image is the same image. What you see inside of it is about the distribution, not the dimension. The dimension is fixed. You see, that's squares that you see, those are fixed. That's the image that you're, for example, you transfer. What we are saying here is that you are transforming from this to this. What you see those colored are this technically.
Like it's just a combination of a couple of Gaussian, right?
That's correct. So most, well, if you think about it, if you think about mixture of Gaussians, on the right, on the top, that's mixture of Gaussians.
Yeah.
Right? So you're basically saying that I have this simple distribution, but I have a really complex data over like let's say face of celebrities, right? We have an image of that, we will see it. And when you look at faces, there's all sort of characteristic concept in the image, like colors, eyes, smiles, nose, and stuff like that, right? In order for me to learn to generate, I should be able to learn those concepts, correct? So those concepts, they generate in a higher dimension. Basically, they generate this really complex distribution over the data. Your goal is that to go from here to that complex distribution. Because if you know that, right, then you also can go backward. Right? From an image says that what was the, if I have an image of a smiley face of a guy, can I go from that to a smiley face of a woman? Can I do the interpolation among? Right, so you can do something like that if you learn this. We're going to get to those ones, right? But that's a good point. That's not the dimension. That's the concepts, I think.
Important features. More red means more important or more prominent.
No, I think that's around the. If you think about the contour plot,
Yeah.
the density, the more so the more red means more. More basically features around there, more points falling over there. Yellow is kind of like a less, and white becomes lower, and the blue is missing nothing. Kind of like a color. It's like a higher the density. So if you think about it, I have a. So we have something like this, let's say, okay, and in basically what we are saying that if you think about from mixture Gaussian, this is technically something like this. Let's say technically two Gaussians, correct? And each Gaussian has a region that has the highest density, right? So if you, right now you plot this in a 2D as like a contour plot, so basically you have this, and then you have this, right? And what we happen here, you have a lots of dense which is in this region and this region, and then as you go becomes smaller and smaller. Right, so that's for the mixture of Gaussian. So that's what basically you see with it.
What changes while learning?
What is changing while we're learning? So what we learn is that this function that we have that is mapping z to x has a parameter theta. That's what we are trying to learn. Theta. If you want to, this function technically we will say is a neural network, right? Is a neural network that's responsible for basically do some transformation for us, or types of basically types of models. What we want to do is that, well, we don't know those functions at the first, like the parameters are just random maybe. So we want to be able to learn those parameters. And that goes back to the couple of slides back that we had. What is the optimization goal? Finding the theta, or this is phi, like to find phi somehow that maximizes this total likelihood. So you basically solve for that.
So how do we find the optimal concepts? Like?
We get there. All right, we get there. We need to define the cost function, and then using the cost function, basically we did it. But in order to get there, we need to first define the architects. All right, let's take a short break. We stopped on this one, and then we continue from there. So
That is still possible.
so this was the basically in the generation past direction, and this is the inverse of it. All you need to do is that to basically apply an inverse. You already got their coffee. All right, you apply the inverse, and if you have one, so this also kind of like make it easier, because if you have one of these, like if you already calculate this gradient with respect to z, in order to find the gradient with respect to the other one, just move one over this. It's just they're like inverse of each other. If you find the gradient, because this gradient function, if you think about it, It's might be not easy to calculate. So if you found this one, you can find the gradient of the reverse by doing just 1 over that, okay, inverse gradient. Because the relationship between x and z becomes inverse, right? So now let's go back to this definition of normalizing. Basically, we wrote. Yeah.
Correct or not? That again, colorful, beautiful thing. Yeah.
You like it because it's colorful.
I think in the nature, this normalizing flow, it's doing the same thing as VAE, because VAE, we go from, let's say, a higher dimension to latent space, and we assume that latent space is the dimension of important features. I think that this neural network at the end learns how many important feature is there and generates this reddish.
So that's a really great point. Their similarities, 100% they're similar, right? They're not the same, they're similar. They do similar concept. They're latent variable models. That means they want to go from Z to X, right? In VAE, you have data, you using an encoder, you encode it, you find some latent dimension that from that latent dimension distribution, you should be able to sample and generate the data again, correct? Here, there's a difference. You still have a similar concept. You learned in the distribution, but in VAE, you break the data.
Yeah.
You go from original large dimension to a smaller or to a higher dimension to reconstruct. Here, you don't break the data. It's the same dimension transformation. It's kind of like you still learn the distribution because you need to learn that in order to be able to generate. But here, you don't break the data like what you do in VAE and sampling from some latent dimension. Here, you have a latent dimension, Z, and you sample from that and you produce this. Again, in VAE, you have this encoder to reach to this, basically. And then you sample from this to generate that. Okay, kind of.
Yeah.
In here, you don't do that. You have just simple distribution. And instead of having a non-deterministic mapping, I'm going to have one deterministic mapping over the same dimension between Z and X. Okay, so conceptually, yes, they do similar things. They're learning that distribution because you need to learn that. But how they do it is different, basically. That's the idea in normalizing flow is I don't want to have an encoder decoder. I want to do direct transformation, basically. Does that answer?
I'm confused. So here we don't have any encoder.
There's no encoder decoder. It's just one network of generation, basically. You know, it's kind of like a basically it's just one type of network. You want to basically data goes through it. I sample from Z and pass to this architect, and that produce and Z is fixed, like either Gaussian or uniform, right? So and from that I should be able to basically to produce X. In encoder decoder, the reason we have encoder decoder is that because we need to, I have the data, I don't know Z. So I need to encode it to find Z and then regenerate it. Here we don't want to have that flow. We just want to pick from something really simple and generate the data from that.
What if, I'm just throwing a stone into that, okay? So what if like we connect these both concepts, like, I'm just imagining this. Please let me know if this is correct or not. So let's take the concept of VAE and normalizing flow and connect them in parallel. How? Let's take an input X and let's say this X to Z also takes in the concept of this normalizing flow, which is X equal to F of X equal to Z. And the inverse is also true for the, let's name it this as an encoder unit, which produces Z, and we take this Z and we again produce the X. Like we are using two separate normalizing flow units to generate X, Z, and also we come back to X again. What if we do that?
So think about what we do in encoder decoder. Like, you have two concepts, generation and then density estimation, correct?
Yeah.
So in order to do generation, you basically go from Z to X. Correct? That's a generation, the decoder. In the basically the density estimation, you want to go from X to Z,
Yes.
right? So, or even you can think about if the X is here, you go from X to Z. So here you need a two architect, basically encoder, decoder to do that, and you want to train them together.
Mhm.
In normalizing flow, what we say that what if you have this Z and this is series of steps and models like a transform invertible that produces X. So if I go this direction, it's giving me if I go this direction, gives me that. I don't need to have different architect and mapping something to Z sample from it to get that. I just need straightforward architect that if I give it a Z, it gives me an image. And it can given the image, it could give me back the Z that I have. Like so, I don't say that what you say, I don't know exactly how does work,
Oh, yeah.
but
So my, the image I have in mind is like, rather than we giving the model a uniform distribution or any circular Gaussian distribution to start with, I'm saying, let's connect it to an unit. I'm not saying even the encoder unit, just another transformation unit, which transforms the original data into a good embedding unit, like I'm borrowing the term, but the data, which is the representation of that, the input to unit for the normalizing flow, which
so sorry. You are saying that instead of having Z come from this simple Gaussian,
Gaussian
you
distribution.
want to have a model that breaks X to something, and from that you generate Z. So that becomes VAE, but it's not normalizing flow. The idea of normalizing flow is that I don't want to do this. I want something simple. I want a model that if I pick from a Gaussian, simple Gaussian or uniform, gives me data. I don't want to go through what I went through with VAE. What you say is technically a VAE.
So not effective or
Yeah.
not useful.
Not that not useful, it's just that all these models are useful, but it's not in this context of normalizing flow. Like a VAE is different. So, yeah, so this is basically the same thing that we had here. But just we try to find this that maximizes this term, and we could do the minimizing of log of this term minus basically that. So that's the objective function that we have. Now, so all of this, so this is the objective function, right? And if you think about it here, you need F. That's the function that does the transformation thing, right? Now, how we come up with F? That's becomes the important part of the problem, and to actually make the normalizing flow practical, to actually work, there are certain basically criteria that you need to basically keep in mind. And that's around the flow model requirement and then basically network requirements, right? So it's not, you cannot just use any type of neural networks basically. You actually, there's certain types of neural network you can use here. So from the flow model requirement, basically, that comes back to what you say. The requirement of the flow model is that Z should be simple distribution. It cannot come from a complex distribution itself. It should be a simple distribution, can enable the efficient sampling. What you see in VAE is not an efficient sampling because you need to basically go through all these transformations, right? And it should be tractable, which VAE wasn't also tractable, right? So that's from the model perspective. Then you basically need to be sure that whatever transformation you apply is invertible. When you do invertible, you also need to keep in mind X to Z gives you the likelihood. You need to be able to calculate that. Z to X gives you the sampling. And so whatever you use, it should be easy to sample, to generate. And same time, it should be easy to reverse it. Right? It shouldn't be challenging. It shouldn't be difficult. Now, then it comes around this efficient Jacobian determinant. The problem with determinant is, what's the cost of determinant? OD3. right? So determinant of Jacobian is not cheap, okay? And if you think about it, in every iteration, forward and backward, you need determinant of Jacobian. And now if you have lots of data and you try to learn, every iteration for every data point, you need to do OD3 forward and OD3 backward, right? So that becomes pretty difficult to train these types of models, right? So the question here is that, or the basically requirement here is that, do a basically more smart or like a smarter way of selecting the functions. You want to select your functions, that transformation that, if, for example, if we say x equal a times z, this a, which later you take a Jacobian of this and determinant over that, you want to pick a somehow that Jacobian has certain basic characteristics. Either is diagonal or is like a triangular instead of being a full Jacobian. So, can basically talk about that. So maybe. Yeah, so let's first have something like this. Yeah, we have that. We'll get. We'll get to that slide. So I was about to write about the Jacobians, but we will get to that slide. Okay, so that's from the model overall, basically the requirement that you have for flow models. But now it comes around the layers that you're using, those function, that actual function, what I can basically use to for normalizing flow. So there are certain requirements for this network that you need. First one is expressive. Expressive means that whatever network you're using, it should be able to map a simple distribution, Gaussian or uniform, to a more complex distribution. So it should be a strong, basically, types of model. It's expressive enough, okay? Then it's invertibility. That means that, well, you need to be sure it's invertible. You cannot pick certain types of basically models because they're not invertible, certain types of layers, right? So it should be an invertible layer. For example, maybe a convolution, because we have the reverse of convolution. But I don't know if you can do for LSTM, no, because you cannot do the reverse over those ones, right? Then the other thing is that efficient inverse computation, the inversion also, so you use the Jacobian in two places, forward and backward. You always have the determinant of Jacobian. However, when it comes to inversion, inversion only exists in one part, in forward flow. So when you basically, reverse flow. When you do the likelihood evaluation, X to Z, you need the basic inversion. You don't need it for the forward, but both you need the Jacobian. So you need to keep this in mind from the cost perspective. I always have a Jacobian and determinant, both forward and backward. So that's a separate cost. Then if I do backward, that means the density estimation, I also have inverse, which it has its own cost, basically. So whatever solution you pick, you need to keep in mind it cannot be expensive because it's otherwise becomes really challenging for learning. Now, there are different types of basically invertible networks that are common in basically normalizing flow. It's like one of them is called linear flow. Then we have element-wise flow, coupling flow, autoregressive flow, inverse of autoregressive flow, residual flow, and contracting maps, basically. So these are common architects that we use in normalizing flow. They are all like invertible, and they all have pros and cons, which we're going to basically talk about and how we can use those. Question? Okay, first one is linear flow. So linear flow is it's types of basically network that has the following form. So H stands for the same Z, basically latent. Or the hidden. So a function that gets this hidden and it gives you a value using this, which is a linear combination. Beta is some like a bias term, and there is this Ohm matrix basically, and then you have H. Right, so that's a linear combination basically. Now, if you think about it, so you need to be able to take a derivation of this F right, for the Jacobian, and the derivation of this is the same thing as this matrix that you have. So the determinant of that matrix, it becomes really important. So by default, if it's just a normal square matrix, then you have OD3 for that determinant, right? That's the cost that you have. However, we can basically come up with different ways to make this types of model basically cheaper. And those are kind of like, think about this choice that you pick, what you're picking as a function or as matrix like that own basically value, it could lead to more efficient basically calculation. So first one is, what if we pick this matrix to basically somehow that the Jacobian basically becomes a diagonal. So let's say we have this f of h function, and this kind of like a linear. So that means the way that we pick this f of h, when you apply it, it technically applies to every dimension of f of h individually. So instead of across all, it just applies to individual dimension. So you have this function, again, the function doesn't matter, it's like a linear function that applies to individual dimension. So if I have something like this, if you calculate the Jacobian is going to be 0 everywhere except for the diagonal. It's going to be a diagonal matrix. Why? Because if you take a derivation with respect to, or Jacobian with respect to h, becomes this one with respect to h, h1, second one with respect to h2, and so on. So this becomes gradient of f h with respect to h1 all the way to f h with respect to hd, and 0 the rest, right? So now you have a Jacobian which is diagonal. What will be the determinant of this?
Multiplication.
Diagonal multiplication of diagonal values, right? So the cost of that becomes OD from OD3, right? It becomes much cheaper. However, there is a challenge here. The challenge here is that this means there is no interaction across dimensions. Every dimension is independent of the rest. There's no interaction among them, right? Because it's all zeros. So that's one way to do it, is having a diagonal, basically Jacobian, but that comes as its own cost. That means that you don't have much interaction between your dimensions. The other one is that, well, what if we do some sort of like orthogonal matrices? Now, yes.
So like, what does that limitation mean in a general sense? Like, if there's no interaction between the different dimensions.
So
what does that translate to?
Think about you going across pixels, and you're basically assuming that every pixel is independent of each other.
Oh,
The color of this pixel is not independent of the next one. It's kind of some idea. But it will work for certain types of problems, but not for complex ones. It's really simple. So the other one is idea of the orthogonal, basically Jacobian. Well, orthogonality, there are a couple of ways that we can enforce that. One of them is actually using this rotation matrix. We saw this in the transformer chapter. So if we have this matrix A, which is cosine theta minus sine theta, sine theta, cosine theta, right? If you have this matrix, that's a rotation matrix, right? So you basically have you have this. Let's say I have this z, maybe z as z1 and z2, right? And you basically multiply this by that. It's kind of like it does some sort of a rotation, and it gives you x, right? Now, if you think about this one, this matrix, the Jacobian of this is equal to itself, right? So it's A. The determinant of the Jacobian, or determinant of A, becomes cosine 2 minus sine 2, which is
cos 2
1, right?
plus
right? This minus that, right? Which is 1. So the Jacobian of this matrix, the determinant of this Jacobian is 1. What does that mean from the learning perspective? We know that probability of X equal probability of Z times inverse of that determinant, right? So if this is always 1, what does that mean? Probability of X becomes probability of Z, right? So this one becomes volume preserving types of transformation. So the volume doesn't change, it preserves the volume directly, right? So, so that's one example, is using a rotation matrix. There is a types of matrix actually called reflect, or reflect, or matrix reflect. It's -1, 1, 0. Yeah, I think yeah, -1, 1. It's called a reflect basic matrix. So what it does, it technically rotates over one axis. Because if you think about, I have Z, which is Z1 or Z2. If you multiply Z by this, technically what you get, X is minus Z1 and Z2. So Z2 remains the same, Z1 becomes negative. So it's kind of rotates over one axis, basically. So it's reflection. This is kind of what for rotational reflection. So that becomes another one. So this one also, so this has a Jacobian of 1. This one will give you determinant of 1. This one give you determinant of -1, right? But it still is volume basically preserving, comes 1 over absolute value of that. So, and yes.
What does the volume preservation translate to?
So what does the determinant tell you? Volume of the matrix, correct?
Right.
So we basically say that P of X equal P of Z times 1 over this determinant, correct? So 1 over determinant, inverse of determinant, what does it tell you? If the volume is large, inverse of it becomes small, correct? So now if this is always 1, because think about it, if volume was large, then inverse was small. Then you multiply a small by P of Z. So P of X basically becomes smaller. If volume was small, the inverse becomes large. You multiply large by this, becomes larger. So volume is changing for X. It's not the same. If this is always 1, the volume doesn't change, preserving. Volume remains the same value.
No, I'm asking, what is the impact of volume being preserved?
Well, that means you're not stretching on you remember the image that we saw, the stretching or expanding? You don't have that impact.
Right, got it.
Like you always if the bean is this size, the bean is going to remain the same size. It doesn't going to become larger or basically wider or shorter.
Can I say something just? I think this rotational thing doesn't do anything, honestly, because we are starting with a normal distribution. And this rotational thing is like changing the coordinates to a polar system or like cylindrical systems, because that's the same like cosine, theta and stuff. It's just you are putting it in a circle. So because that's spherical, like shapy at the beginning, doesn't make sense what I said?
No, it makes sense. Well, so what he's saying is that if you think about this, the Z has come from a spherical Gaussian. What he says is that if I rotate it, that rotation doesn't have any impact. But the volume is preserved, but the rotation doesn't mean that the values are the same. Positive becomes negative, so this is different values. So so this again, what we are seeing here is that most of this volume preserving and stuff like that are still an approach, but they're not the best approach across this. We will see as we go. But these are ways to make the cost of this transformation cheaper. Okay, there is another one called It's called actually householder matrix. You just. Maybe I just leave it for you to read it on your slides. But there is another type of matrix also that gives you this orthogonal that's called householder matrix, basically. You have it on this slide, just leave it there so I don't make you confused. Let's go to now the third one is the triangular matrices. And the triangular matrices basically means that we want our Jacobian to be either lower triangular or upper triangular. One of these two basically scenarios, depending on the result that we get. Now, if you think about triangular, let's say this is a lower triangular, and this is Jacobian. Remember what's every element in the Jacobian means? Is derivation, right? What do you think this tells you about the dimensions or the features? No, so it's not symmetric. So it means these are all zero. You only have the bottom.
The image that we get at the end is somehow symmetric because for example, the derivation of f of x1 with respect to
correct path, you're on a correct path of f, but drop the symmetric idea, but you're on a correct path about the derivation. So Jacobian takes you about the derivation of that function with respect to individual dimensions. So if, when I calculate this derivation, these are like this zero, only have values on the bottom. What does that remind you of?
Is that even possible?
What was that?
Is that possible?
If it wasn't possible, I wouldn't write that.
Jacobian being lower triangular or upper
Yeah.
triangular?
kind of masking.
That's masking, GPT. Every dimension, every word, only the derivation has with respect to the previous words. There's no forward values, right? So that's the same thing in the GPT you have, right? It's like always zero. So that means if you want to have this triangular version, well, the cost becomes OD2, but it becomes some sort of like an autoregressive flow models. Because now only every pixel that you create, the function that you have, this f of z becomes f of zi, or z less than I. Only indexes comes before can go to the model that will produce that xi basically. Okay. So we will see that further. But in order to have this triangular, it could be upper triangular or lower triangular, you need some sort of like a masking idea. So now the bottom line basically says that, well, the challenge of all this is that linear flow alone cannot transform a normal distribution into arbitrary distribution. Because if you think about it, it's like everything is kind of linear. It's like a kind of like a volume preserving. It's hard for this model to cannot actually transform into complex distributions. So in order to do that, we need to basically introduce a different types of basically model also. And the next one is called element-wise flow. And the idea here is that, well, since the linear flow is not sufficient, let's use a different strategy. And the element-wise flow, the idea behind it is that let's break down the data into some like elements or some like sections. We don't have an image for it. So let's say I have this image, and in the idea here becomes, well, let me break it down into section, for example. Okay, and each one of these are separate elements, for example. It's kind of like I want to go through this. Now, f of h, that function becomes functions over each element separately. The function over first element, second element, or second section, and so on. Okay. So because of that, well, this Jacobian also, if you think about it, this Jacobian also becomes diagonal, right? So because it's just individual element, they only have their own basically function. So the derivation doesn't have interactions. So this becomes the determinant of the Jacobian. It's efficient, but as we said before, it doesn't have a mixture among dimensions. Now, there is an example for this one. It's like a piecewise linear mapping. So the way that this basically works is that, let's say you have an example and you want to break this example into k sections, for example, k parts or elements. And in the piecewise linear, this is the equation for the piecewise linear mapping. F of h will be calculated using this. Now here, phi or theta, obviously it's technically phi, but is the parameter that you basically select. And that parameter comes from some sort of like a distribution. It's like a probability of this, probability of this, probability of this, probability of this. It's kind of like a distribution. So that term basically gives us f of h phi equal the summation over bin. So B stands for the bin number. K is for the number of basically sections that you have. You have over K. What else we have? Plus H is basically the hidden that you have. K is again the number of bins, overall that you have. You have minus B, which B is the bin times this this value. Now, B itself is calculated using this term, HK plus 1. Is it plus 1? Yeah. Okay. And what you see H is around HK is just a floor function. It means if you just float, just bring it to a floor. So there are a couple of things about it. This image will summarize this. So let's say in this image, so you broke down your data into 5 chapters or 5 sections. Each of those sections will have a corresponding phi value. And those phi values, their probability value, they should sum to 1. Okay, so you have 5 basically probability per section, they will sum to 1. Using that, basically the function that you have, because it's monotonic, it becomes like this. So this basically a slope that you have is corresponding to the phi value. So whatever is your phi, the slope is kind of like that also. Kind of like a linear. So now basically what we are saying here is that in order to find for a given h, for example, if you pick this cyan color, this like a bluish color, and you want to find the function of that, so you technically need to say f of h2 given by 2 technically comes from something like this. In order for you to solve this, you're missing something, and that's b. You don't have b by default. You need to calculate b. And b comes from this equation. Okay. So what you need to do is that you basically say that, okay, b equal whatever is the h value times k. K is 5 because we have 5 sections. And this is kind of like a float plus 1. Okay, so this gives you some number. And that's between that 0 to 5 technically for the number of bins. Okay, so that defines which bin basically you need to use. So let's say this gives you 3. Okay, so then when you want to calculate this equation becomes summation over 3 minus 1, k from 1 by k plus, again, h times 5 minus b. What was b? Let's say 3 plus 1 times phi of b. B was 3, that means phi of 3. Okay, so that basically goes through this. You find the value, and whatever you get, it becomes this line that you have over there, basically, the value for that line. So this is basically called piecewise linear mapping. Okay, so it has a fixed formula, and you just need to divide your data into section and then operate over them individually. The difference here is that, well, all these sections are independent of each other. There's no interaction among those.
Can you give us a little bit of feeling about H? I don't get what is edge exactly.
Yeah, I can give you one example. Might have. How it could. You have a good example. Just let's assume H is so H and Z. Let's say your could be your Z value, right? So you have this Z is a vector, and you break down this vector into chunks. Okay, so first 5 element of this vector becomes H1. Second 5 element becomes H2, and so on and so on.
Just a numerical approach to
Yes.
like
Yeah. So the next one becomes coupling flows. And coupling flows basically, it has a same flavor of the previous one that we saw, which you split the data into chunks. But here we are going to apply like a different transformation. So in coupling flow, let's say in this example, you see 2 chunks. So we splitted the data into 2 chunks. So this hidden vector becomes H1 and H2. The first thing that you see is that H1 has a direct mapping to H prime. Okay, whatever transformation you apply is direct mapping. Okay, and the inverse of that is also direct. However, when you want to calculate the second term, you need to couple it with the first term. So that's becomes the coupling flow. So the second term, in order to calculate H2, there is a function here, this G, which need to be invertible. So G need to be invertible because you see it's invertible. This G gets H2 as an input and input over this, the output from this one also. Okay, so that goes here plus H2 goes to G and you get H2. Now, the way that you can look at it is I have this neural network. Okay, and I'm going to call this phi HI. So I have this neural network. When I pass an HI to it, it gives me something. Okay, it's a scalar vector or something. Then I start with here. So I have the H1 part of my hidden vector, and this directly gives me H1 prime, like the is identical mapping. Then when I want to calculate the mapping for H2, what I need to do is 2 things. First, I need to pass H1 to this neural network. This is some arbitrary neural network. And I say that, hey, I gave you some vector, tell me what you learned from it. Give me your learning. So this network will give me some learning. Then I bring H2 itself. So I have this, I have H2 and this learning from this network over H1. I have 2 information. I pass this to a function G, which should be an invertible transformation. Only a function that I can reverse it, basically. And that gives me H2 prime. Now, if I had the H3, then this, H2 will go to this network, comes back, goes for H3, and so on. So you couple the information as you go down. You start on top from direct mapping. So first part of the data is just directly the same thing, and the rest basically kind of like a feeding to each other. Okay. Now, the important part here is that the neural network doesn't matter invertible or not. It could be any neural network. Because you're not inverting this, you're inverting this. That neural network gives you a scalar or something and you pass the scalar here. So this should be invertible. You don't care about the neural network to be invertible or not. There's just a neural network that gets the data and gives you some output. That part does matter. You back propagate over that network to make it better, but the inversion doesn't matter. It's just you want this to be inverted. That's the important part. Because this maps to this reversion. Does that make sense? Which part?
How does the neural network not being invertible not affect the
So there's a neural network here, correct? I give a vector to it and it gives me a number between 0 to 1,
Okay.
right? Whatever the number this gives me, I put it here in this function. And what is this function? Let's say I have my function g of x or g of hi equal hi plus 2 times the output of that neural network, correct? So this neural network output gives me a number, a scalar, right? So something plus some number. So you should be able to invert this, right? So it doesn't matter what's the neural network because you just put the output of the neural network here.
Okay.
What you select as this function should be invertible. If you pick something that this combination is not invertible, then you cannot solve it. Neural network is just a way for you to condensing, learning from the previous time step or previous step on top and couple it with what you have currently. I get some information from above, add it to what I have, pass it to a function, get something new. This should be invertible, not that doesn't matter, just feature extraction. You can call it as like that. Yes.
So the phi is only depends on H1, not H1 prime.
Just H1.
So what exactly is? We convert H1 to H1 prime
That's for the forward pass.
and we can backward it because it's a function that's can be.
Yeah, it's just basically same backward from H1 prime to H1, just same direct mapping. This is independent of this flow. This is just for the below flow. So this doesn't even see H1 prime. They're not connected to
So
each other.
you're saying that for the second step, we are using some knowledge from the previous
Yeah,
step.
knowledge over H1, not H1 prime. Knowledge over the raw data. Basically, so I have this image and I have segmented. The first couple of pixels that I have, directly I put it back here, let's say. Then when I want to go to the second part, I pass this pixel to a neural network and say that, hey, tell me what you see in it. Maybe a CNN or something. Then I share that information with this one. So that, hey, this is what we saw in above, or this is the information we extracted from above. Does that answer?
Yeah, thank you.
No question on your side? All right, so
It looks like sir, one more. Why are we even like trying to upgrade linear flows? Because they are very basic. Compared to triangular method, like where we can OD square basically.
I mean,
Compared
they're all-
to them, these are very rudimentary, right? Basic, very basic one. Is the learning even happening?
So this is a great question. The thing about most of these layers is that as we go through these are layers, same types of layers that you saw in deep learning class. When you see a dense layer by itself, you don't use it maybe, but you stack it after convolution or stack it after CNN or LSTM, and then it works, correct? These are the same story. You learn how these layers can work, and then you need to put them on top of each other. You need to combine these together, basically, right? And as we go through them, you will see this combination among these, basically, network types.
If there is H3, we won't give any information about H1 to it.
That goes to the next types of the model. We get there. All right. So, okay. So here, just to summarize here, so you splitted the basically input into two parts, and you said there's this transformation. And one of them is directly, the other one is basically going to be invertible.
One last thing, Professor.
Yeah.
Sorry. So with the stacking, the complexity rises, right? Kind of like the neural network backpropagation happens, and with the stacking of next layer, the complexity increases, kind of.
So, yeah, so let me create. So when I say stacking, it's not the same stacking that you will see. It's just combination of the model. Wait for me. Let's go through this slides. You will see that.
Okay.
Like you have coupling flow, you have basically what you saw linear flow, and you see the next one combines coupling flow and linear flow into new things, basically. And it's just very. Okay. So for the coupling flow, what you saw here, you can also think about the Jacobian. The first part of the Jacobian is going to be the 1. So normally whenever you have this coupling flow, the top left corner is 1 because it's linear, the direct mapping. There was no interaction between the other one, right? But when you go to the basically the second part or lower part, then you have actual gradient because there was a relationship. Like this one was just direct mapping, so the gradient is 1. But the other one has a combination basically, so they have gradients. So it's kind of like a half basically Jacobian. Now, so actually there are a couple of important things here. So one of the things that we do in coupling flow is that in order to create some sort of like a generalization across data, we apply some permutation to the data. So that means that we permute the data, actually, the data that you have, or basically the features that you have. That permutation in the image, we use in something like a convolution. If you think about convolution, basically just the permutation, right? So basically you apply some sort of like a convolution, and that local convolution goes and basically creates some sort of like a permutation for you. And you use that in order to basically add more generalization to these types of model. Instead of just having to be splitted, you apply some sort of permutation among those, so then it works better. It's more generalized. Now, this is an example of permutation matrix. So any matrix that has the following form, that every row and every column will be 1, sum to 1. It's basically is 1 and then there is 0. Every row, every column, that becomes permutation matrix. So if you apply this one basically here, this permute basically in the following form. Okay, so that's just an example of permutation. And the determinant of this is always 1. That means is volume preserving again, because the inverse of determinant also becomes 1. So now the next one becomes nonlinear, basically independence component estimation, or NICE. Basically, that's the term for this normalizing flow. It's one of the ones that when it came out, start to generate really good quality, basically, data overall. So the idea basically of this NICE was that, well, it started by having some sort of an additive coupling basically layer. So you saw the coupling layers. Now this one had another version of coupling layers, becomes like an additive coupling layers. So you, instead of basically just breaking the data and goes to a neural network, and from a neural network goes to the next one, basically you have this equation that first part, same thing, identity mapping. This next part basically becomes a function over the Z that you have, the H that you have, plus, and basically this M, it is a neural network over the Z, okay? And then you basically, you can reverse that in the following form. So Z goes this becomes minus this one. This becomes the gradient. Now there's the gradient becomes a bit different. So here you don't have 0 anymore. Why? Because if you take a derivation of X, this term, with respect to Z, which is, this is the gradient. So if you take a derivation of first X with respect to Z is 1, I, okay? Now this term, the second line, with respect to Z, there are 2 types of Z. Z's prior, Z after. So with respect to the Z after is 1, okay, or I. With respect to Z, this should be I, N1, this should be N minus C, yeah, that's from N minus C. So D plus 1 through N becomes N minus C. And with respect to this one, becomes the derivation basically of this term, right? And that's this derivation of this term with respect to that Z only. Okay. So in the previous version of coupling flow, you had I, and then you have some derivation, and there was no interaction in the gradient. So here, there was no interaction. In this one, there is an interaction because the way that the formula basically works. Okay. So now, so this is the first step in NICE, a NICE model. Yes.
I just have a question. Can you please go back 2 slides back to the coupling flow? In this I still don't understand because G3 is again, it includes some learning from H2 as well, right? Because you pass it to a neural network, that'll be phi of H2. So why is the gradient with respect to H2 is 0 in the Jacobian matrix?
Gradient with respect to,
For the element 3,
Okay.
it's a function of again the learning from the previous layer and the current layer, right?
I see. So you're asking for this one.
Yes, yes.
So that's a great question. So you have G with respect to H3 Jacobian, and then we have Jacobian with respect to H2. And so this is not a map to this image. This image should have 2 parts, only 2 sections, not 4. It's just an if G is element wise. So this is not exactly that image that we have. So this image here will have 2 gradient become 2 by 2, right? But still go back to what you're asking. I think it's it's possible that we need to have values here. Actually, it does says Jacobian is triangular with identity in the top left quadrant. So it should be triangular actually. So it's not, that's correct. It shouldn't be 0. Okay, yeah, so that's a great catch. So that shouldn't be 0, it should be triangular. So
This one is representing where,
this is just an example, says that if G is an element-wise flow, this becomes kind of like this. It's not for the previous image.
okay. No, like I'm saying, if this was to be represented in this kind of image form, would it be like, okay, the first layer just directly, first 2 layers don't learn anything. Then third one learns, so first 3 don't learn anything, and then the fourth one learns from the third one. Would it give like a similar
What do you mean the first 2 doesn't learn anything? You mean the direct mapping?
direct map?
Yes.
Okay.
So here in this example, this section of the image has 2 parts, and these 2 parts are direct mapping. The next section has 2 parts. So in NICE now, in basically the next one, the idea is the same. There's the first part of the NICE, it does the same, it's a coupling flow. It just does the exact same thing. But it also NICE basically says that, well, we know the coupling flow has a problem. And the problem here is that, well, this is going to be the determinant of Jacobian is 1 is volume preserving. We don't want volume preserving because volume preserving becomes the same as the linear ones. It doesn't learn to map to a complex distribution. So what we do in NICE, or the types of model, has a second basic architect at the end of the model. And this is the second part. So the first part of the NICE is the coupling flow. The second part of the NICE is called rescaling transformation. So there is one final layer in this NICE basically model, which what it does, it multiplies whatever Z you got so far by a matrix S. Okay, and that matrix S is responsible for a stretching or a scaling part of the work. So you know by default the coupling flow doesn't do that because the inverse of the determinant is 1, and you always P of X becomes equal to P of Z. So in order to stretch it, you introduce a matrix S and transformation basically that multiplies by Z to give you X. And that should be basically invertible. So that means you can go back from Z to X to Z by dividing X over S basically. So that becomes the final layer of the NICE model. It's basically a rescaling of Z. On that? You just think about it. You on the last layer, you have this matrix that you multiplied by whatever H1 prime and H2 prime you got in order to scale, stretch it, or compress it, basically. So this is just example of what we generated basically with NICE algorithm. If you think about just the quality in compared to what you saw in last slides for the VAE, is much higher from the image generation perspective, right? So now the next one is called real NVP. So this is another type of basically normalizing flow and basically non-volume preserving extension of NICE. So we know in NICE was volume preserving. We added that final layer to translate it to basically scale that volume. So in this NVP, which is just, you basically hear, mainly you hear the term real NVP as a types of model. It's the idea is that we want to be sure from beginning is non-volume preserving. And in order to do that, we basically changed that function. So in the other one, basically in NICE, this formula was, this is equal to Z plus a mu over previous H. Here that we are using a different function. The function basically says that X comes from the current Z, the current slice that we are at, plus, multiplied by, or element-wise multiplication, exponential over the output of this basically network, plus you pass this also to another network. So you have two networks, a mu and you have an alpha network. Both of them, they get the Z from the previous layer. So these both networks, you have this network mu phi, and then you have this network alpha, let's call it theta, it doesn't confuse you. So this goes here, this also goes here, gives you two values. You pick those two values, put them here in this equation, and multiply them by this. That will give you this value, H prime 2. Okay? So, and the inverse of that also looks like this, basically. You can write from that X to Z, that's Z to X. Then the Jacobian of the forward mapping, which is this is the forward mapping. Oh, sorry, this is the forward mapping. Z to X, sorry. I was like this, okay. Jacobian of the forward mapping, take a derivation with respect to Z. The first part is always identical because it's just identity matrix. The second part, you take it, if you take a derivation, it still has two parts with respect to current Z and with respect to the previous Z's. So this is for the previous Z, this is for the current Z, right? And the basically determinant of this Jacobian also always becomes the multiplication of diagonal because the upper diagonal is 0, right? So because multiplication of this terms, because this is I, so multiplication of this term. So this is now the result that basically real NVP generates. So much higher quality from the generation perspective. And these are all, the beauty of these types of models is that, well, these are basically, these are like invertible. It means you can basically go from here to here and just reverse back. Can go from one image to all the way to Z. And what we will see is that later we can also interpolate between images because the way that we learn those more complex distributions. So you should be able to also interpolate among those. So now this becomes the interpolation, and this is the result generated by real NVP. So what you will see here is that you have 4 images on the left. 1, 2, 3, 4. You use a formula like this, the Z equal this random formula that you can assume, and that will produce this. These are interpolation steps among time, basically. So it combines these 4 together to generate something from the distributions that it has, basically. So here, the same thing. Here, same thing. So it allows for interpolation because you learn about the distribution, you learn about these features. So you can do a direct mapping, and you should be also to combine those together. Found that? No? Does the interpolation make sense?
No.
Which part?
What exactly does it, I mean, I don't understand in
So,
those 3.
you have 4
understand the
images,
phrases.
correct? You have 4 images.
So the input is only the 4 images.
That's
on the
correct.
right.
Look at the
Okay.
equation. Z1 for image 1, Z2 for image 2, Z3 for image 3, Z4 for image 4. So you have 4 images. You interpolate those 4 images to generate new image.
So phi and phi prime are learnable.
Learnable parameters. or interpolation basically parameters, something. So in one step, you generate this based on whatever phi and whatever z you had. This image converts to that.
So phi and phi prime are exactly the parameters that we calculate in previous step in generation.
No, these
step.
are separate. These are interpolation parameters.
How is the training in this part?
So, I mean, I really don't know actually how's it the training, but I can assume something like this. So I want to be able to combine features or basically images, learn something that it has a high possibility of being an image, for example. That means if I go from this image to another image after interpolation, it should look like an image. So if you can calculate the density of it,
We have to have the complete set of images on, for example, top left, and train the model based on that and say, this is the interpolation that we want. And then we calculate the phi and phi.
could be. I don't think for interpolation, you use a supervised approach because I think this is unsupervised technically. You have image, you interpolate them, and then if you can compare that image against some probability, say that, is this a probable data point? If you get a yes, then you're like, that was a good learning. If you get a no, then that's not a good combination, basically, right? Because if you think about it from the supervised perspective, you need to combine features and you need to label those. Like, there is no label, if you think about for this. But what makes sense is that if I could pass this image to another model that says that, hey, is that possible? This is an image. If you tell me it will give you some value, some probability. If the probability is higher, that means the interpolation was good. If probability is lower, that means the interpolation was bad. So, and you try to basically learn using that, something like that. And I haven't done any interpolation, so I might be totally wrong in this.
So even in this, we start with basic uniform distribution or Gaussian, or we start with something
In what? In
the training process, like
interpolation.
training that's model, like the
Real MVP.
real MVP.
That's normalizing flow. Is always same thing.
Always same thing.
Yeah.
So the leftmost 4 images. Yeah.
This is a different
Okay.
problem. This is not a real MVP. This is interpolation. You already have a real MVP model.
So that's what, like,
Yeah.
so in the training process, like I'm talking in that. So let's say I have these 4 images, I give the model as an input. So it learns and then the interpolation is
No,
different. Like
you have learned the model.
Oh,
Done. You're
I
done.
already have a model.
This could be your project. You have learned the model. You pick a model. You bring images, give to your model, and say that, let me extract the features that you have. Let me see how I can combine them
Oh, okay.
to build new features, new images from that.
New images.
This is not the training. This is interpolation over what the trained model has, basically.
Got it.
Okay, so then it comes to autoregressive flow. And now, as the term autoregressive comes, that means things is going to be sequential. You're going to slowly fit to the model for the next pixel, or maybe next couple of pixels. So the autoregressive flow combines the coupling flow with an autoregression, basically, concept. So start with the same thing. However, H1 doesn't give you H prime direct mapping. It goes through a function, invertible function. This goes through invertible function, gives you that, so it should have invertible backward. Then still you have that some neural network that doesn't matter, it's just feature extraction. Gets H1, you use that, pass it to this G function with H2, create H2 prime. Then you go to H3, you pass you pass this H2 to this neural network, same neural network. You basically, it has 2 information, this neural network, H1 and H2. Create something, you add that with H3, continue. So it's like at every timestamp, you get the current hidden layer, plus you have this neural network that gets all previous hidden layers, condense them together, you pass that information to this invertible function, and you create H4.
The same across all of the batches.
Yes.
Like,
Same invertible basically function here. So, and then this basically becomes invertible, it should be always invertible in the other direction. And here again, you don't care about the inversion on the neural network part. So it's just similar to the coupling flow, it just becomes an autoregressive version of it. Also, the last line basically says that there's also something to remember. Autoregressive flows are universal approximator for probability distribution. If you actually can make it, it gives you exact density estimation or exact approximation for the probability distribution. Just exact one. So like other models types like VAE, GANs, diffusion, they are not, they don't give you the exact. This gives you exact distribution if you basically make it happen. This becomes example of continuous autoregressive flow, which the idea basically is like a really similar. So this is the definition of autoregressive, and you basically sample a Z from a Gaussian, and let's say you have n steps, n pixels, for example. You sample nzi basically, and then you pass the first one to this formula. You give x1. Using the x1, you pass it to this neural network, mu2 and alpha2. Whatever you get, you're going to use it here, and sequentially you basically continue. So this every step you create different x using basically continuous autoregressive flow. Now, basically that comes to basically next thing, which was the flow interpretation. So think about this one. We are going to see like 3 types of model over this image. Okay, so the way that here this works, this is like in forward pass, in generative pass. So you have Z. At any time, if you want to create an XI, this types of model requires 3 information. One is the current hidden state, okay, or current latent Z that you have in order to create Xi. Then it needs 2 other information, alpha I and mu I. Alpha I and mu I, it's some, like I have some network that will be generated over previous data, not previous hidden layers, previous data, previous X's that I created. That means if you think about this part, this side on the right side to be X, in order to find alpha and mu, you use the previous on the right side, plus only the current left side, which is the bottom of the image. So only the current left side and over the previous one. Well, the challenge that you can assume with something like this is that in this forward, or it's actually like a masked auto regressive flow. The challenge with something like this is that the forward pass is not going to be fast. It's going to be slow. Why? Because every time when you want to generate a pixel, you need to have previous pixels completed. So you cannot do basically parallel processing. Right? It becomes sequential like an autoregressive, so it becomes super slow in the forward direction. Does that make sense? In the backward direction on the other end, this model basically, you already have all the X's because it's a backward, then you can parallelize this. Just at one go, you can create all Z. Why? Because Z comes from this equation, Xi minus mu minus exponential of alpha. If you already have all the X's in a parallel way, you can find all of this, and you can find all of this basically at the same time. So the forward, which is the generation, is slow. The backward, which is the density estimation or the inversion, is fast. Okay, so this is about the mask autoregressive flow. So the forward becomes slow, the backward becomes fast. But these are like in strong types of models. Now, the idea was that, well, could we improve this? And they came up with a basically inverse version of that. It's called inverse autoregressive flow. So the first one is called MAF, mask autoregressive flow. This is IAF, inverse autoregressive flow. And the only difference here is that they swap the order of the dependency. So in the forward pass here, when you want to go from Z to the image to generate, for every pixel, you don't need to wait for the previous pixel to finish. So because every pixel doesn't depend on previous pixel, it depends on previous hidden layers. So if at first you have Z randomly generated, all of those, so at the same time, you can basically create all the pixels in one shot. In the previous version, MAF, this was reversed. If you look at the image, in order to calculate X, you depend on X's on top. You see those blue bars on top? Here, you only depend on the bottom. So Z is the random data that you have. So if you have it, then you can just parallel compute all of this and do one go. So the forward pass in IAF is quick. You can quickly generate data. However, now the backward pass becomes the slow part because, well, you rotate the generation. So now the backward pass becomes the slow part. So the idea here was that, well, how could we, I'm not talking about this equation because this is just simply an example of how you use that formula that you see, which is exponential of alpha Z1 plus mu. Okay, I assume that you can go through that yourself. But you have a question? What we want to do here is that, well, there are some trade-off between MIF and IAF. So in MAF, fast likelihood evaluation, slow sampling, the backward was fast, the forward was slow. In IAF, fast sampling, the forward was slow, the backward was basically, forward was fast, backward was slow. And depending on what you want to do, if your goal is to do generation, you don't care about the density estimation, then probably you just go with MAF. In IAF, because fast sampling, I can quickly generate. If you care about density estimation, your downstream task is density estimation of a data, then you go with MAF. And if you basically need both of those, like can we combine those? And that's where the types of model, I don't know if you have heard of it, parallel wavenet, that becomes the basic combination of MAF and IAF. So parallel wavenet, it's the types of model that looks like this. And this combines, it has this idea of like a teacher-student network. So there are two types of models here. So on top, you have a teacher model, okay? And on the bottom, basically, you have the student model. So think about it from the perspective. So a student model gets Z, this vectors that you generated, like a random basic vector that you have, goes through this student model, and a student model basically creates this Xi, like the output becomes Xi, like the data, generated data. Then you also, that same data, you can ask from the student model, what is the probability of that data given Z? Because it generates it for you, right? You can answer that density. Then you pass the data that was generated by a student model to a model called teacher model, which is a pre-trained model. So this is a pre-trained model. This is a model that you train. Then you say that what is the likelihood of this data? So the teacher model is the base larger model, gets the data generated by student model, and so you say that, tell me how likely is this image? How good is this image? This teacher model gives you a probability. Then you pick that probability, compare with this probability as a Taylor divergence, and you train this one as like a feedback loop. How good was your generation? Because I asked, you gave me a basic generation, I give it to a teacher, and the teacher it's bad, and you need to go work on it. That becomes the feedback. So that becomes the parallel, basically, wavenet. So, I don't know if we have might have something. What's that? Okay, so here, just to match it, so the teacher model is MAF. So what was the properties of MAF? Fast inversion, fast density estimation, is not good for generation. So you build the teacher model to be a strong model that if you give a data to it, it's not good for generation. But it's good that if you give a data to it, it evaluates it for you and says that how good it was. Then your student model becomes the opposite, IAF, good for generation, slow for density estimation. So you first have this teacher model basically trained using MLE, a model that can find the density basically. You have that trained. Then when this one is trained, you initialize a student model and you basically start feeding random data to the student model, says that generated image. You pass the image to the teacher model, get some output, use a KL divergence, update the student model. So the teacher model is fixed. You're not training that, or the pre-trained large model, for example. And that's basically the same. That's just a KL divergence between whatever generated by the teacher model, basically, versus the student model, student and teacher. Any question on that? So this does the combination of both two, like MIF and IAF. And it's just overall training algorithm, basically train the teaching model, then train the student model after. Now this is just an example of also what a normalizing flow actually can basically enable for us. This doesn't happen in other models like GAN, diffusion. They are not able to approximate the actual probability distribution. But a normalizing flow, it can give you exact computation over the distribution. So they are pretty strong for finding the distribution, like the density of that data. This was the training sample. This is what the model learned. This was the training sample. This is what the model basically learned. So they are doing a really good job in finding that probability density. That's what they're pretty strong. So they're good for density estimation. And if you learn the density, they are good for anomaly detection also. So, and this is just another version of the normalizing flow. It's called GLOW model. And this is just an example. And this is basically interpolation from one phase to another phase, basically, this model does. So it's capable of, based on the prompt, to change the data from one phase to the other phase. And this is happening by learning those features, those distribution among characteristics, or the like the features of the phase. So you can just interpolate among those based on a query. And so this is the GLOW model. This is the architect of the GLOW model. We're not going to go over that, but it has series of coupling, basically layers. It does a one by one convolution, which enables for that permutation also. It does downsampling, it does multi-scale flow, dequantization, and basically the sampling. So this model basically creates the GLOW model, something like that. Okay. So it's basically high quality types of model, but it still lags behind GAN. GAN still has higher generation quality basically between images. And last thing, last two slides that we basically say that the normalizing flow are pretty good for finding the density estimation. So one thing about is that on top, basically A and B, they are together, C and D are together. So if you have this sample data, and this is the data that you have, and this is what the normalizing flow learns, and using the minimizing the KL divergence, you try to learn that. And you can basically improve that by going to a different version of it, basically. And that becomes the combination of normalizing flow plus sample. Instead of doing a KL divergence between this and probability of X, you do a KL divergence between this and Q of X, basically. So if you directly, instead of, so technically think about this like a teacher model, target distribution, like the larger distribution, student model. So instead of in one, you're just focusing on this, learning this, and the other one, you're focusing on learning the target distribution, the KL divergence. Now, we don't want to go over that, but as we say that this normalizing flow are pretty good for finding that there's actual distributions. And these are two version of how you can basically apply something like that. All right. And that's the same thing, the scale divergence. All right, I'm going to stop here. First, any questions? I know. I can see when the